So we have been trying to understand the पीले चॉक्स रखे पीले हाँ थैंक यू All right. I would start by reminding you a couple of things that you saw in a Carnot engine or a Carnot cycle. I think what I did prove the last time was कि अगर आपके पास एक कार्नो इंजन जो है वो बना हुआ है in some such manner with points A, B, C and D here and V on this side and pressure on this side, and therefore you have VA, VB, VC and VD, then we worked out the last time, and you will see, check in your notes of the last lecture. मेरा ख्याल है कि that is where we were in the last lecture, कि there is a relationship among the volumes like this. है आप सबके नोट्स में ये मौजूद कि ये रिलेशनशिप एग्जिस्ट करता है और इस रिलेशनशिप को हमने यूज़ किया था ये इस्टेब्लिश करने के लिए कि मैं पेजेस जो हैं आगे पीछे हो गए अब सब All right. Let me go back a little, maybe a few steps, and take it up from there. आपके इस isothermal process में दो processes हैं, 1 and 3. इन दो processes में work is being done and heat is being transferred. In the process 1 you have work what we call W1, this one, and 3 is here, and 2 is here, and 4 is here, and Q is what we call QH, and I am putting these signs of magnitude to say that we are at the moment trying not to get too specific about signatures. All right? Some heat came in from here and some work was done on the system. And this is done by written this way. Similarly, W3 was the same as QL. There was heat QL going out here, and there was heat QL being given to the system. And also, you noted that W1, I'm going to only write the result that we had derived was that for an n For an ideal gas running in a Carnot engine, this is equal to nRTH times log of VB divided by VA. W1 was equal to this. We had worked it out. W1 was equal to this. And W3 was equal to NR times lower temperature TL log of VC over VD. VD over VC? Is that with the signature also?
Yes, sir. VD over VC.
With a positive sign. Okay? All right. मेरा ख्याल ये है कि ये ठीक है लिखा हुआ ये. Hold on a sec. I'm just following the expressions that I have over here. Let me go back now. मेरे पास जो लिखा हुआ है वो ये है कि V1 is minus W1 is minus nRTA times log of this, and W3 is written as minus NR etc times VD over VC. Okay? ये लिखा है आप लोगों के पास. चूंकि यहाँ पे मैंने मॉड लगाया के साइन लगाए हुए हैं मैग्नीट्यूड्स के, तो इस वजह से सिग्नेचर्स जो हैं वो मैंने ख़त्म कर दिए. ऑलराइट. अच्छा, जिसका फ़ायदा जो है वो ये कि आई कैन राइट दिस QH and QL in this particular manner, जिसका मतलब जो हुआ कि QH divided by QL is equal to TH times log of VB over VA divided by TL log of VC over VD. And because I have said that this equation holds, this relationship among volumes, therefore this is equal to TH over TL. Now this is a very, very important relationship in our conceptual the conceptual development of thermodynamics from here onwards. So QH over, so for us the important relationship is QH over QL is the same as TH over TL. I could, in fact, with the signs that I should, sign of magnitude that these things should carry all the time with them. All right? In fact, I will turn this into saying that QH over TH is the same as QL over TL. No big deal. I just rearrange them. In fact, this is what I should have done right over here. And since we know that QH and QL are always in the opposite direction, one is given to the system, the other one is taken out of the system. Therefore, I can easily write over here QH over H is E minus QL over okay. Now this is a very important step over here. I have written QH over TH minus QL over TL is equal to 0. And starting from here, I will prove a very important thing about the second law of thermodynamics.
So यहाँ magnitudes important नहीं
जी
So यहाँ QH और QL के magnitudes important नहीं है modulus sign
नहीं okay नहीं because of removing the modulus sign I have been able to put this minus sign here. Okay, if I had taken care of them, certainly I would have eventually had a minus sign over here. The point is that because QH and QL are always in the opposite direction, therefore one of them has a minus sign, and therefore when I take one part of it onto the other side, I will get this negative sign. Oh, I'm sorry, plus. So nice of you to remind me this is plus, because it is on the other side it is this part, this will be one of them, this will be without the mod signs, they will be equal to minus of this, and therefore this plus this is equal to 0, is equal to 0. That is an important equation from where we will get some results. Okay. So in a Carnot cycle, the sum of these two terms is 0 in a Carnot cycle. The important development after this is when you try and generalize this result to any closed cycle. And not just the Carnot cycle. Okay? That is what we are going to do now. For any cyclic process. Now, what we will do is we will take a cyclic process, any cyclic process, which goes from point A, say, point A to point B, and then comes back. We may not need these points at this time, but there is this cyclic process. And what we will do is, we will do a mental construction over here. We will draw a number of isotherms on this. A number of isotherms on this. And then approximate these points where of the curve by adiabats. Okay? So, certainly one can have as many isotherms as one likes. And what we have done is that we have approximated this particular curve by an adiabat, or we just drew an adiabat over there. Although this part of the curve was not adiabatic, but we just made an adiabat over here. Okay? So in this exercise, what happened is that I have turned this whole process into a large number of Carnot cycles. Okay? So turn into a sequence of Carnot cycles. We remember that Carnot cycle is a very, very special process. And it is a very, very special process primarily because it has these adiabatic parts. These adiabatic parts during which no work is done, but then the work cancels out on the two sides. Total work done is 0. And the amount of work that is done from in this whole entire cycle is the sum of the work that is done at the top isotherm and the work that is done at the bottom isotherm. So that is what is true in this case also. So this is a sequence of Carnot cycles. So traversing if you go on this particular cycle, and if you think you have a very large, going on this particular, traversing the cycle AB, A is nearly the same as traversing over these Carnot cycles. Do you see this point? If you are going this way, it will be something like going along these paths. Let me take an example. If I were to take a Carnot path like this, and then another one which comes like this. This is generally nearly the shape that I have in this particular diagram of two adjacent Carnot cycles. So I have two adjacent Carnot cycles here. You see, these isotherms are common between them. And the amount of heat that comes out from here is, while it is the output of this cycle, it is the input for this cycle. Okay? While the output for this cycle, it is input for this cycle. The amount of work that is being done over here gets transferred, is done over here, and so on. So eventually, what you have is a series of these cycles, and the entire cycle, the entire cycle gets approximated by a sequence of Carnot cycles. What is the advantage of that? The advantage is that the traversing the whole cycle A, B, and then coming back to A would amount to something like being Q1 over T1 you can conclude from this that this I don't know how many of them, all of them, and then using that relationship that we have over here, sum of all of them would be equal to 0. All right? you can make use of this particular property of a Carnot cycle and sum over all of them, Q1 over T1 plus Q2 over T2 and so on and so forth. Sum of all of them will be equal to 0. Or you can write that sum over I, Qi over Ti is equal to 0. And therefore, in the limit of infinitesimally narrow cycles, infinitesimally closed isotherms, we will have actually a statement that will say that dq over t over a closed cycle is equal to 0. Right? In the limit of infinitesimally closed isotherms, when the difference between them is terribly small, then one can make this statement, this discrete sum of terms like this, into a closed path integral of this quantity dq by t. All right? And it is important here because we know, since any state function, all functions of a state xi are such that integral dxi is equal to 0, which means that they describe a property of a particular point in the PV space. So we have therefore a PV space, PV diagram. A particular point describes a particular value of pressure and a particular value of volume, therefore a particular state of the system, and a function of a state will have a value over here, right, for each particular point, and that if you take it away to some other point and then come back to the same point, it will have the same value. It doesn't really matter how you went, how far you went, and how did you come back. As long as you come back, the value of this point is going to be the same. This is described by this is the state of a system, and therefore it describes this property of the state of the system. And therefore, for any function of the state, this particular property has to be satisfied. Right? Any doubts? Any questions? Any? ये t कौन सा है? Any t of the system that will be given by some t value, not necessarily. Right. So it will be the t. अभी मैं इसके ऊपर यहाँ पे मैं बताऊंगा कि ये कौन सा t है. आपका कहना यह है, इनका सवाल जो है वो ये है कि आप यहाँ पे इस t को कौन सा t बता रहे हैं. यहाँ पे तो आपने एक इंडेक्स लगा दिया था. यहाँ पे आपने ये बताया था कि किस आइसोथर्म में आप बात कर रहे हैं, है ना. यहाँ पे तो आपने वो बात नहीं बताई. लेकिन जो what I'm trying to do over here is that I'm trying to define a quantity which will have this particular property, and I will tell you what t it will then describe. Okay?
Sir, but heat is not a state function.
T?
Heat.
Heat is not a state function.
but the quantity you are defining is.
Is. All right? So the important point that he has made over here, observation, is that Q is not a state function. You cannot define Q for a point in this diagram. You cannot. Q is what comes and goes, right? And dq therefore is not something which is, in other words, but Q would depend upon path, how you go and how you come back. Whereas this particular function is path independent. So Q is path dependent, yet dq by t is path independent. Okay? Whenever any quantity like this, a particular function xi satisfies this particular property, then xi is path independent. Okay? I thought I should remind you of this. This is path independent because you can go to any, if you want to go from this point to this point, you can choose this path or whatever path. The difference between them is given by that difference that you have. For example, if suppose I have the difference between this and this point is, this is x1 and this is x2, and difference is dx x1 minus x2. Then going from here to here, by whatever path you choose, the difference is always going to be this. So it is path independent. And it is the relationship between this and this statement is very logical, because if you can come back to the same point after having traversed by different paths and the value is the same, and the value is 0, then you actually have assigned a particular value to this particular point. Okay? So path independence means that when you come back to it, you will get that equal to 0. Or you can say, if you can get back and the value is 0, then it doesn't really matter how you went and how you came back. Okay? So path independence follows from this particular property. And therefore, what we have over here is that dq is path dependent, but dq over t is path independent. That is a very important point in our discussion. We therefore have reached a particular point. We do not know how it, we have sort of, all of this development took place slowly. We have come to see that dq by t must be a state function. Function of the state, as I wrote over there, as a function of the state. Q must be, dq by t must be a function of the state. Which function of the state? We know of pressure, we know of temperature, we know of internal energy, we know of some other quantities, perhaps volume. And this is something which is completely unknown to us. We don't know what it is. This is the first time we have come across a function like this, which is a function of a state. And this is what then was given the name of entropy. And it turns out to be one of the most important concepts in physics.
So would this have the same units as the heat capacity?
It will have the same units as the heat capacity, you are right. Joules per Kelvin, yes.
But that's different from entropy.
Yes, it is different from entropy. Okay, we will entropy has the same units as heat capacity. Heat capacity is a particular response of a given system, like iron, like cobalt, like wood, like steel, to supplying heat to it. How much of heat it can take for a given rise in temperature. Whereas this particular quantity is a function of the state. It will have different values on this PV diagram. It will have value S1 here and S2 here and S3 here. It will have different values at different points in this space, in the space of variables of things. Okay? Any other question at this point? No. Okay. So this is where we are, and we say that, look, we have now defined a new state variable that was not known before this, and we call it entropy.
Entropy is a variable or a function?
Well, state variable and state function are the same thing. State variable, state function are the same thing. Okay? So I will be using it, alternatively. So on reversible paths, you see on this PV diagram, we have these Carnot cycles on reversible paths. We did discuss reversible processes and irreversible processes a little bit earlier, but we haven't gone into details of them, and I think it is going to have a very important meaning over here. I remember that a few lectures ago I talked of reversible and irreversible processes. I can't find it now. Yeah, I did. I do find it here. As I said, a path is reversible if you can retrace it and go back, and a path is irreversible if somehow energies have been lost in the process of going from point 1 to point 2, so that you can't actually come back. Retrace your steps and come back, because you have been losing energy in the particular in the process. So this particular path that we took, AB, was reversible path, and Carnot cycles are defined for reversible paths. So on reversible paths, what we have shown is that if you take, for example, ds, okay, I haven't said s is equal to, we will define this variable and we will say, we will name it s, ds as dq over t, okay? And you will define s to be an integral over this ds. And we take them over two independent paths. For example, path 1, I had made them here. If suppose I have, I start from point A and I go to point B on on two paths, path 1 and path 2. Then ds A to B on path 1 is the same as plus b to a ds is equal to 0 is the meaning of this statement that integral ds is equal to 0. So that statement is translated into this statement, and this statement amounts to taking over this path a to b and b to a, coming back. And this is on path 1 and this is path 2. And because I can write b to a ds as minus a to b ds path on path 2, I therefore have a very important relationship, which is that a to b ds is the same as a to b ds on path 1 and path 2. So exactly the thing that I was trying to explain over there. Ji?
Right side of the path.
Right side of path? Sorry?
So, sorry.
Okay. It was initially going from point B to point A, and I have capital A over here and capital B, capital A and capital B. I should be consistent, so it is A here and B here. Initially I took a circular path to mean A to B and B to A, and then I showed that B to A is minus of A to B, and therefore this is equal to this, so it doesn't really depend on path, it is path independent. Okay? And entropy therefore is defined in terms of change in S, which is SF minus SI, final state minus initial state, which is integral I to F of ds. When you integrate, which is the same thing as integrating from initial to final state of dq over t. This is true in the general case of reversible paths. I'm lost everywhere now. Where are my papers? हाँ, मैं भी एक मिनट में आपकी बात सुनता हूँ. ज़रा मैं देख लूँ कि मेरे पेपर्स डिसऑर्गेनाइज्ड हो गए हैं यहाँ पे. All right. G.
So you said that the Carnot's cycle is based on reversible path.
Yeah.
So but what about the energy lost in the third step, isothermal compression?
Why? Okay. This is Carnot cycle is on a reversible path. So if I go back to that particular diagram, some energy is being taken from somewhere, and some energy is being delivered to some place, and some work is being done in one case, and the other work is being done in the other case. Okay. So in one case, heat enters into the system. In the other case, heat leaves the system. In the first case, work is done by the system. In the second case, work is done on the system. Okay? This is what we went through. In the entire process, there is no other loss of heat. Heat only goes in to perform work, and the rest of it comes out as an accountable heat. It is not lost somewhere. So it is therefore there is no dissipation in this. So it's a reversible process. So her question was that, reversible processes, how would you, in this particular example, if you say that reversible process, that Carnot cycle is a reversible cycle, what would happen to the heat lost? So the heat lost was actually, it's all accounted for. It is not lost. It is not out of the accounting.
So would this mean that any cycle would be reversible because the heat is always accounted for? It would never be completely destroyed?
No, but then some heat is not recoverable. Accounted as well as recoverable. The heat that is coming out over there is usable. As you see in this particular example where the heat coming out from here is usable over here. Coming out from here is usable over here. Whereas in the dissipative systems, that heat which comes out, a large part of it is unusable. The one that we say would give rise to irreversible processes. Okay? There was other examples of irreversible processes also. Other examples of irreversible processes, since we are talking about it, so let me spend a minute on it. We have the simple example of a glass of water, and you put in a drop of ink into it. It just goes and disappears, okay, coloring the entire water. Now that particular process of a water going in and mixing is something which we call an irreversible process, okay. It is a process which you cannot reverse. You cannot get a glass of water with ink already mixed into it in a situation where you can extract out the ink, okay, without having to do any work on it. So that is an irreversible process. Similarly, you can think of many such examples. If you have, for example, an example that we will see over here, and also you may have seen in your earlier chapters. If you have gas completely filling this particular part of this compartment, this compartment of the box, and then allowed to escape into this, the gas will simply go and then occupy the entire volume, this volume plus that volume. Remove this compartment. This particular act of spreading out into the two compartments, is an irreversible process. You cannot reverse it. You cannot get all the gas back spontaneously on its own into this particular part. Okay? So that is why. So you have to make this distinction of reversible and irreversible.
So we only consider the spontaneous processes for reversibility.
You cannot get back the same thing spontaneously. Yes. Okay. In many situations where there are various situations in which with some amount of work you can certainly get the situation back. For example, if you have a glass of water and if you throw in a bit of ink, then perhaps a little bit of titration and so on and so forth, you can get back your drop of ink out of this water. But that is not what you would call a reversible path taken by.
That was what I was asking. We only consider the spontaneous reactions for the.
Right. And that is what the spontaneous processes which define how some directions are allowed in natural processes and other directions are not allowed in natural processes, is all that is at the essence of the second law of thermodynamics. Okay? So we are getting to it slowly, defining the second law of thermodynamics. Okay? Here I would take a quick, to give you a feeling for calculating entropy. I have an example over here. Ice cube. You have an ice cube. The mass of the ice cube is 10 grams. Okay? Any other questions? This one? So what is the question?
I and F जो आपने integrate
हाँ,
किया, I to F. What is I and what is F?
Oh, what is I and what is F? Okay. When I said change in entropy in a particular process which went from an initial state to a final state is entropy of the final state minus entropy of the initial state, which is integrated from initial to final values of entropy. Okay? Of any variable, but in this particular case, over here, of some of the variables that are defined over here. We will see in some examples where you can actually you can know what initial and final values are and which values are to be integrated over in some of the examples that we have. Okay? Now, let's take this example of an ice cube of 10 grams in weight. This is usually the weight of an ice cube, right, that we make in our refrigerators. And we allow it to melt at T equal to 0. T equal to 0 means what? T equal to 0 degrees centigrade. Right? It should melt at T equal to 0 degrees centigrade. But because we have defined this expression only for a reversible process, so we will have to think of this melting as a reversible process. Now this is very tricky, reversible melting. You can't have this. Normally melting would be regarded as an irreversible process. But one can think of some conditions in which this melting could also be reversible. Suppose you have this cube and if you are trying to melt it, you will have to connect it to a heat bath. And if the difference of temperature is very large, the melting would be certainly irreversible. But if the heat bath is very, very close to 0 degrees centigrade itself, only very slightly higher than 0 degrees centigrade, the ice cube will get melted because of the temperature being over 0 degrees centigrade. But then this difference is so small that as soon as it has melted, one could actually go back and turn it back into ice. So you see, for example, in some situations like if you have a cube of ice or any block of ice, and you put a thread or a wire on top and press it, it sort of the ice melts, and the thread or the wire gets into it, and then the melted water becomes ice again after that, so that you can actually thread the wire or the thread into the ice cube. You can always do that. So this is possible. It is possible to have a reversible melting. Now we have this situation, and you would like to know the entropy for this change of entropy. Now for this change of entropy, we would need to know the amount of heat that is consumed in the process. And therefore, the amount of heat we would need to know. For this, we will need to know the heat of fusion, a constant, latent heat of melting of water, of ice, or fusion of water. This is 333 kilojoules per kg. with this, then, you can make the Q, the value of Q is mass times latent heat, which is mass is in kilograms 10 to the power minus 2 kilograms. Is it okay? It seems that, things are not very clear. Fine. Okay, 10 to the power minus 2 kilograms. And then I have multiplied by 333 times 10 to the power 3 joules. And then that's it, because kilogram cancel out. And therefore, this is 3330 joules. Heat capacity, therefore, is quite well defined now. Temperature, of course, somebody asked me over here what this temperature is. Which temperature shall we talk about? In this particular case, this takes place at 0 degree centigrade, 273 Kelvin, and therefore S is this Q over T, and that will be 12.1 or 12, nearly 12 joules per Kelvin. Now, when this ice cube melts, there is this change of entropy. I should put this as delta S, and this Q means delta Q, and I would put this delta Q over here. Otherwise, I would not be making much sense. This is increase in entropy. So, change in entropy is actually increase in entropy. And what happens to the environment around it? Environment means that there is a heat bath which gave heat to the ice cube for this melting, and this heat that came in was exactly the same amount. The temperature was exactly the same, nearly the same as you said, and therefore environment also gave this heat minus 12 joules per Kelvin, because it gave heat to the ice cube, and therefore total net delta S was equal to 0. It was 0 because of this condition of reversible melting. Okay? Next, what we should do is try and extend this discussion beyond reversible processes. So, defining entropy change, describing entropy change in non-reversible, irreversible processes. Most of the processes that we see in nature around us are irreversible processes, and therefore we should know how entropy changes in irreversible processes. Only then shall we be able to formulate a law. That law would be, we are still waiting to define that particular law. That will be the second law of thermodynamics in terms of entropy. Okay? There's a very good example that one can take. In fact, I talked about it a minute ago over here, this particular example. Let me take this example of a process we know is irreversible. This is an irreversible process. So we have a box which is completely isolated with a partition in the middle and all the particles filling up one part of it. Okay, so there is this volume, we will call this initial volume V1, initial volume V1, temperature T1, all right. The box is completely insulated. So in this particular process, dq will be equal to 0. And here we are in problem. We see this problem because if dq is equal to 0, how would we calculate ds? Because we have defined ds in terms of dq. We have defined ds in terms of dq. So if dq is going to be 0, then how are we going to write ds? Yes.
Example above is the temperature of environment also 0 degrees Celsius.
The upper example?
Yes.
Okay, his question is, can you repeat the question?
Says is the temperature of environment also 0 degrees Celsius?
Okay, the question that he asked is if the temperature of the environment is also 0 degrees centigrade. No, you see in this particular example, when I tried to define reversible melting, I said a melting would be reversible if the heat bath, which is the environment for this system, is only at a slightly higher temperature, not at a much higher temperature, so that the melting is something which could be reversed. And therefore, the heat bath temperature is nearly close to 0 degree Kelvin. Okay. In this particular example, where we wanted, this is something like an example which only is meant to give us a tutorial on how entropy changes are calculated. We will have many other examples coming in also. But in this particular example where we think something reversible can happen, we just calculated this. And over here also, I think this was also possible because there is no change in temperature, because this is happening. You see, this is happening with a latent heat. This is happening when there is a transformation of phase from liquid to solid or solid to liquid. Okay? At that particular point, the latent heat is what gets consumed or given out. Okay? And that is what we used over here. Not a specific heat, sorry?
Then in reversible processes, the net change in entropy is approximately equal to 0, not exactly 0.
In the irreversible process? In the reversible processes, the net change in entropy is 0.
Exactly 0?
Exactly. You see, when we will define the law, we will say delta S is greater than or equal to 0. That will be equal to 0 for reversible processes and greater than 0 for irreversible processes. Okay? But we will see these things with some reasoning later on. Okay. Where were we? So coming back to this particular point, okay, here we are. We have a gas filling this half of the box, and the box is completely insulated, and we remove this partition, and the gas will fill in the entire box. In your in the book that you studied, this is called free expansion. Okay? The point is that over here in Fourier expansion, we are confronting a problem where we say that dq is 0. If dq is 0, how do we calculate ds? This is the problem that we are grappling with at the moment. Since it is a free expansion and dq is equal to 0, free expansion means no work. No work because the gas comes out and fills up the other compartment without doing any work, without lifting any weight, without pushing any piston. It simply comes out and fills up the other case. So there is no work being done. So dq is 0 and dw is 0. No work done, no heat leaves or enters. And therefore, from the first law of thermodynamics, we have du equal to 0. Yeah? क्या चीज? नहीं, कोई प्रेशर की वैल्यू थी, 0 तो नहीं हो सकता ना. वर्क डन कैसे हुआ? नहीं, वर्क डन इस लिहाज से हुआ कि चेंज इन वॉल्यूम हुआ ना, मगर साथ ही साथ प्रेशर भी चेंज हो गया. तो दोनों चीजें चेंज होने से इन दी ऑपोजिट डायरेक्शन, नो वर्क वॉज डन. अगर आप इंट्यूटिवली सोचना चाहें कि कैसे हुआ, लेकिन इसकी जो असल रीजनिंग है वो ये है कि it didn't push any piston, it didn't perform any work on the outside environment. Okay? Is that still a problem in understanding? Yeah. क्या हुआ? आइसोथर्मल अब दिखाएंगे हम कि आइसोथर्मल हो जाएगा ये. यस, नाउ वी विल शो that it is isothermal because du equal to 0, and because du equal to 0, therefore dt is equal to 0. When the gas expands, even temperature doesn't lower in free expansion. Okay?
Why is it not an adiabatic?
dq is 0. Why? Sorry, आपका सवाल है कि ये एडियाबैटिक क्यों नहीं है? वो तो है. हाँ जी जी, ये फ्री एक्सपेंशन जो है, फ्री एक्सपेंशन in an environment which is completely closed, there is no heat that leaves or enters, no work is done also. In that free expansion, temperature doesn't change also. ये वो वाला नहीं है जो आपने पहले देखा था ना कि एडियाबैटिक एक्सपेंशन जिसमें वर्क होता है उसमें देयर इज अ कूलिंग. एडियाबैटिक एक्सपेंशन लीड्स टू कूलिंग, है ना? ये वो नहीं है. ओके, यस, इट हैज वैक्यूम, क्योंकि कोई पार्टिकल नहीं है पहले. वैक्यूम का मतलब यही होता है कि कोई पार्टिकल नहीं है पहले उसमें. ऑलराइट. क्या चीज क्या होगी?
एक्सपेंशन से पहले और बाद में स्टेट सेम होगी.
स्टेट नहीं, स्टेट वेरिएबल देखे ना, इसका वॉल्यूम जो है वो एक्सपैंड कर जाएगा. V1 था, V1 से वॉल्यूम 2V1 हो जाएगा गैस का. ऑलराइट. प्रेशर कुछ था इसका, वो मुख्तलिफ हो जाएगा प्रेशर डिपेंडिंग अपॉन the equation of state. टेम्परेचर वही रहेगा मगर प्रेशर और वॉल्यूम तो चेंज हो सकते हैं ना. ठीक. ओके, सो देन वी मूव ओवर हियर. यहाँ पे हमने जो शुरू किया वो ये है कि एंट्रोपी चेंज इन इरिवर्सिबल प्रोसेसेस हम डिफाइन करना चाह रहे हैं, जबकि हमने रिवर्सिबल के वास्ते हमने कर लिया था पहले. इरिवर्सिबल के लिए हम क्या करेंगे? असल में इफ द एंट्रोपी has to go from point 1. Suppose this is a space of, where entropy is one variable. Entropy यहाँ S है और यहाँ पे कोई और variable X है. Could be temperature, could be anything else. अगर यहाँ पे value S1 है और यहाँ पे value S2 है, तो it doesn't really matter कि आप किस तरीके से S1 से S2 पे जाएं. Since it doesn't matter, क्योंकि ये function of state है, लिहाजा if you can't find it in an adiabatic process, let us find it in an isothermal process. If you can find it in an isothermal process, because this is a state variable, therefore the change in entropy will be the same. Okay? And this is what we will do. Therefore we will find ds in an isothermal process. All right, isothermal process में तो we have already seen things quite clearly. Isothermal expansion में isothermal process को भी मैं specify कर दूं. यहाँ पे process is actually expansion. और isothermal expansion में हमें मालूम है कि ideal gas के वास्ते isothermal expansion में du is 0. Therefore, W is minus Q. Work and heat are opposite to each other. And W, आपको याद होगा, हमने लिखा था W was equal to minus nRT log V2 over Vf over Vi. Right? This is what we wrote for an isothermal expansion. Work in the case of an isothermal expansion. Go back to your notes, you will see this. And Q will likely be, likewise Q will be equal to nRT log Vf minus over Vi. And since delta S is Q over T, therefore this is equal to nR, and since Vf is twice V1 to twice Vi, since Vf is twice Vi, and therefore what we have is only log 2, so nR log 2. This is very important result. T cancel हो गया ना? T जो था यहाँ पे वो cancel हो गया उस T से, and you are left with only nR times log 2. This is a very important result because it shows that if something has happened, initially you were not able to see if entropy change has taken place. Now you see actually that entropy change has taken place, and once you remove this wall and the gas is allowed to fill in the whole volume, the change in entropy is equal to this quantity. Okay, del Q अगर मैं शुरू से लिखता यहाँ पे आपकी बात को मैं ख्याल रखा होता शुरू से, तो मैं यहाँ पे डेल्टा Q करता, यहाँ पे ये और this and this. Is that what you're pointing out? Good. Okay. So here we are. I think this result is something which we will keep in mind when discussing the importance of the significance of the concept of entropy later on. Achha, in this particular case, in the first example, we calculated change in entropy of the environment. The environment had given heat to the ice cube. right? The environment had given heat to the ice cube, and therefore the entropy of the environment also had to be to change, and that we calculated. In this particular case, because there was this insulating wall did not allow any heat to come in and go out. The environment did not give or take any heat from it, and therefore there was no change in the entropy of the environment. Okay? The good thing is that the entropy, if I write delta S environment equal to 0, then total delta S, which is equal to delta S in this case, when you remove the partition plus delta S of the environment, that is equal to NR log 2, which is a positive quantity. This is what we have been saying. Okay? So the law that I preempted, I actually wrote over there and then erased, I think. When somebody asked, when is entropy change equal to 0 and when it is not equal to 0, I said in the reversible case, it is equal, change in entropy is equal to 0. In the irreversible case, it is positive. So law that comes out is delta S is greater than or equal to 0. In a reversible process, it came out 0. In an irreversible process, it came out positive. Okay? Time for a few more questions before we break for the day. सब समझ में आ गया?
जो डेल्टा T की हमने वैल्यू निकाली है NRT नेचुरल लॉग 2, तो ये उस चीज़ को
जरा सुन ले सवाल, एक मिनट, अभी तो वक्त है जरा सवाल
तो ये उसको कॉन्ट्रडिक्ट नहीं कर रही क्योंकि हमने पहले कहा है कि dq इज टू 0.
Oh, okay. Now, you see, इसके अंदर तो dq इक्वल टू 0 है. हमने इसी चीज़ को कि जिसमें एक्सपेंशन इसमें हो रहा हो, हमने एंट्रोपी निकालने की कोशिश की है आइसोथर्मल एक्सपेंशन में, एडियाबैटिक में नहीं, आइसोथर्म जहाँ पे था फ्री एक्सपेंशन, हमने उसकी जगह पे निकाला आइसोथर्मल एक्सपेंशन के वास्ते. ठीक है, इस वास्ते कि हमने आर्ग्यू ये किया कि अगर S की वैल्यू यहाँ और यहाँ वही रहनी है तो किसी भी तरीके से आप करें वैल्यू वही आनी चाहिए. ठीक है ना? तो इस वजह से कंट्रडिक्शन नहीं है उसके अंदर. ठीक, ओके, आई विल सी यू आफ्टर टुमारो.